Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. So this time we gonna do some examples with regard to optimization. So this would be basically the last topic with regard to derivatives, where we gonna basically make use of all the concepts that we have discussed, all the tests that we have discussed together, the first derivative and the second derivative test, in order to assist us with regard to decision making, especially in business and economics. So let me just get the slides on. Okay, so we're going to be discussing optimization. So what is optimization? So optimization refers to problems that involve finding the absolute maximum or the absolute minimum of functions. So in other words, we need to find values that will give us either the maximum of something or minimum of something. So common optimization problems involve, for instance, like finding areas and perimeters, but this wouldn't be under our discussion. Um, it includes maximizing revenues and profit. Okay, this would be closely related to business and economics, because whenever we are given any economic problem, any revenue function or any demand function or cost function and profit function, we would want to find values of inputs or quantities that will give us the maximum revenue or the maximum profit, as well as minimizing the cost, as well as inventory control. Okay, so we're gonna basically do, let me see how many examples do we have. First example is on area and perimeter. So this one, I'm gonna basically leave this to you. Okay, if you have the time, please go through the example, because the principles, the procedures will be the same. We need to first of all identify the objective function, and then we have to optimize it. We need to find the critical numbers, okay, and then use the test or the procedures or from the first and the second derivative test, especially theorem 3 from the previous on how to find the absolute maximum or absolute minimum on the interval given, and the values of x where this occur, and then use the critical numbers, the absolute maximum and minimum that we found, to find the solution. Okay, it's just that with regard to this area and perimeter, instead of using the revenue function or the profit function, we need to use the formula for area and perimeter. So I'm going to leave this example to you. So just go through it, because the application would be the same. The application would be the same. Let's go right away to um, the procedure. Okay, the procedure. So this would be the suggested steps on how to solve optimization problems. So step number one, you need to basically read the question carefully and collect information that are related. So you need to look for, you need to introduce the variables of interest, the variables of interest like revenue, for instance, or a price or quantity, and then look for the relationships among the variables. What would be the relationship between the variables? Because based on this information, you need to develop a mathematical model, an equation that relate all the variables. Would it be negative, positive? What would be the sign, and whether there's a constant? Okay, and then you have to summarize all this information in an equation. Okay, in an equation, so they would be in the form of either to maximize the function or to minimize the function within a specific interval I. Step number two, so once you have done with the equation, with the mathematical model, you need to solve it by finding the critical numbers of the function that you have stated in step number 1. So that's why step number 1 is very important. I mean, if you got it wrong in step number 1, for sure step number 2 will also be wrong, because you need to then find the critical numbers. Step number 3, you need to refer back to the procedures developed in section 4.3. So this is theorem 3. We need to, theorem 3 basically summarizes everything. We need to first do the first derivative and then do the second derivative test, okay, to find the absolute maximum or minimum of fx on the given interval, and the numbers, the values of x where this occurs. And finally, step number 4, we use the solution that we found in step number 3 to find the answer to all the question asked originally in the problem. So don't forget step number 4. This would be the final answer to the problem. Okay, so let's do this example together. So say this is parameter. So I'm going to skip this. Let's go right away to example 4. Okay, maximizing revenue and profit. So let's say we have this example where we have a firm, that a company that sells X, okay, X quantity. So X would be quantity of permanent marker, okay, quantity, each year at a price P dollar per marker. So the price is P. So the price demand equations is given like this. So price equals to 10 minus 0.001 X. So this is the price demand equation. So the question now is, so we have two questions basically. Number 1, what price should the company charge for the markers to maximize revenue? So we want to maximize revenue. So what should be the price? And number 2, what is the maximum revenue? Okay, what is the maximum revenue? So solution. So for the solution, we know that revenue, okay, so revenue equals price multiplied with demand, right? Price multiplied with quantity. So this is our revenue function. And this is the function that we want to maximize. We need to maximize this. So how do we collect all this information? So this variable is already given. X represent the quantity and P represent the price. Okay. So based on this, we know that revenue, okay, equals P multiplied by X. And our P is given here, right? So we simply need to substitute this P. So this equals 10 minus 0.001 X, multiply with X. And should give us 10x minus 0.001 X squared. So this would be our revenue function. The revenue function. And we want to maximize this, right? We want to maximize this. And we also know that both P and Q must be non-negative. They can be 0, but they cannot be negative. So quantity must be non-negative and price must also be non-negative. So based on this, we know that the quantity must be less than or equal to 10,000. Okay, how do we know this? From here. Okay, you simply need to solve for X here. Okay, remember matrix algebra, the linear programming, the inequality. So we have done this before. So make sure you know how to solve for X. Okay, so when you solve for this, you know that X will be less than or equal to 10,000. Now the mathematical model. So this would be for step number 1. Step 1. Okay, we want to maximize the revenue function, and this is the revenue function which we have got from when we do the P multiply with X before. Okay, so then step number 2, we need to find the critical numbers of the function. So how do we find the critical numbers of the function? We simply need to find the first derivative. So what is So step number 2 would be to find the critical, okay, the critical numbers. So how do we find the critical numbers? So we simply differentiate this, find the derivative. So what is r prime of x equals 10 minus 0.002x. Okay, so in your slide there is a typo. This x shouldn't be here. It should be 10 minus 0.002x, and we set it to equal to 0. Okay, in order to find the critical numbers. Remember, critical numbers, okay, will be located when we have horizontal tangent line, isn't it? So that's why the slope is 0. Okay, the slope is 0. So when we solve for this, we should get that. So when we do this, we have 0.002x equals 10. So x equals 10 divided by 0.002 equals to 5,000. And that's how we get 5,000 is the critical number. Okay, the critical number. And next, what is, now we want to basically then use the procedure. So this would be step number 3. So step number 3, we want to investigate, is this an absolute maximum or absolute minimum? So we need to use the second derivative test. So the second derivative test, when we differentiate this one more time, right? So r double prime of x would give us, so this is 10, there is no x here, so 0 minus 0.002. And this is negative 0.002. So we know that this is less than 0. It is negative for all x. Since this is negative, remember second derivative test, we have concave downward. So this is, so based on this, we know that this is an absolute maximum. Okay, absolute maximum. So the revenue would be maximized, okay, would be maximum when the company sells 5,000 markers. 5,000 markers. Okay. Now, has this answered the question before? No, not yet, because we need to find what is the maximum revenue. So the maximum revenue, how do we know the maximum revenue? We simply substitute 5,000 into the original revenue function. So how do we get this? We simply replace x with 5,000. So you get 10 multiplied with 5,000 minus 0.001, 5,000 square. So we get 25,000. Okay. And then when demand is 5,000, the price would be $5. How do we get this? You replace this into the original price demand equation. So you should be able to get all these would be the answers to the question posed in the problem. So the company achieved maximum revenue of 25,000 at the price of $5 per marker. And this is the answer to the question. Okay, so as simple as this. I mean, this is basically the application of all the first derivative, second derivative test with regard to optimization. Okay, so maybe another example, maximizing profit. So let's say the same company, in the previous example, now has a cost to manufacture those markers at Cx equal 5,000 plus 2x. Now we have question, what is the company's maximum profit? And what should the company charge for each marker? And how many markers should they produce? Okay, now to do this, you need to remember basic economic relationship. Profit equals revenue minus cost. So previously we have been given the cost function, the revenue function, 10x minus 0.001x squared. So we simply need to subtract the cost function from the revenue function. And this is how we define our profit function. So simplify this. So when we simplify that, we have, so 10x minus, so this is positive, negative, so we get 8x minus 0.001x squared. There is only one term with x squared minus 5,000. So now collecting all this information, we have our mathematical model as this is our profit function that we want to maximize. And our profit okay, is the equation is 8x minus 0.001x squared minus 5,000, which was obtained when we subtract cost from the revenue functions. And the same restriction, the same domain applies where x must be non-negative but must be less than 10,000 because price cannot be negative. So based on this, so now let's try to find the critical number. Step number one done. So step number two would be to find the critical number. So we if you remember, the profit function was originally from the previous slide. From the previous slide, it's 8x 8x, okay, minus 0.001x squared minus 5,000. So how do we differentiate this? I missed this minus. So the first derivative would be 8 minus 0.002x, right? This. And then we set it to equal to 0 in order to find the critical numbers. So when we set this to equal to 0, we have 0.002x equals negative 8. So my x will equal 8 divided by 0.002, which will give me 4,000. Okay, this 4,000. And it is the only critical number, okay, for the profit within this domain. So now we can apply the theorem number 3, the second derivative test, to check whether this is truly a maximum or a minimum. So how do we do this? We simply need to take the second derivative of the profit function. So what is the second derivative of the profit function? Second derivative, so this so this would be 0 and this would be negative 0.002, and it is negative. So when it is negative, we know we have an absolute maximum because this is concave downward. So we have absolute max. Okay, we have absolute maximum. Okay, so x equals 4,000. This critical number gives us the maximum profit of 11,000. How do we know this? We simply put x here, 4,000, replace this in the original profit function. Okay, and using the original price demand equation, okay, the price is $6. So when we have the cost function now, the price is now $6 per marker. Okay, and maximum, so this would be the final answer would be maximum profit of 11,000. So this would be the value of the profit at maximum, okay, is realized when we produce 4,000 markers and they are sold for $6 each. So this is the answers for the questions posed in example 5. Okay, example 5. Next example, so using the same information, it's just that now the government imposed tax of $2 for each marker that the company produces. Okay, so now we need to, so with the introduction of the tax, our cost has now changed, right? I mean, revenue function remain the same, but cost function, okay, is now changed due to the introduction of the tax. And because of that, our profit function, okay, will also change. Okay, so it affects the cost equation. So our original cost we need to simply add the new tax. So 5,000 plus 2x plus 2x, and this gives us 5,000 plus 4x. Okay, so now the new profit function would be 10,000x minus 0.001x squared, our original revenue function, minus the new cost function, which is 5,000 plus 4x. So instead of 8x, we have 6x, right? 10x minus 4x, we have 6x, while all the others remain the same. So this is the profit function that we want to maximize. Okay, step number 1, okay, within this domain. to find the critical numbers, we find the first derivative. So 6 minus 0.02x. So this basically our x would equal 6 divided by 0.002, which is 3000. So this is the only critical number within that domain. And our second derivative is negative 0.002. There shouldn't be x here. There's a typo in your slide, so get rid of this x, which is less than 0 for all x. So since this is negative, based on the second derivative test, we know that our function, our profit function, okay, is concave downward. Okay, concave downward, and this is absolute maximum. Our profit is maximum. So producing 3,000 3,000 items of 3,000 markers would basically give us the maximum profit. So what is the price now? The price would be $7 each. Okay, $7 each. So the tax $2 basically increase the cost by $2 per marker. The price that they should charge, okay, to obtain the maximum profit is now $7. Okay, an increase of $1 per marker in cost to the consumer over the lower tax model. So the company need to absorb the other $1 of cost. So it is kind of a sharing. So $1 will be paid by the company, $1 will be paid by the consumer. Okay, the consumer. Okay, and this has caused their profit to drop from 11,000 to 4,000. And the 6,000 in taxes to the government would cost the company 7,000 in profit and increase the total cost of markers sold to customers by 3,000. Okay. Um, all the other examples are, the same. I'll just leave the remaining examples to you. I mean, you just need to follow the 4 steps, carefully. Okay, it's just that for example 8, it is an inventory control. Okay, so instead of looking at the revenue, cost, and the profit functions, okay, you need to come up with a different objective function. Okay, so I think just finish up the slides. Okay, so here we are basically minimizing the cost. Okay, the minimizing the cost. So I'm going to leave that the other examples to you. Okay. So I hope these few examples that we have done together, uh, you should be already aware to these different applications of the first derivative and the second derivative test with regard to optimization. So that's all for now. Inshallah, we'll see you again next time. Assalamualaikum warahmatullahi wabarakatuh.